Good morning, everyone. Welcome to the all-new Dr. TLA Plus series in 2017. As you can see that we are experimenting something new today. So we have Dr. Shuai Mu from New York University. He is presenting remotely. Okay, so we can see him and his slides, and he's also able to hear the room and see the audience. So feel free to ask questions and then clarifications during the presentation. And then to introduce Shuai, so I've been personally working with Shuai during last year. And then Shuai and a team from NYU are working closely with Microsoft Research and a real storage team on a highly impactful project. And that's how I came to know Shuai as one of the few researchers who have very deep understanding on both subject of consensus and transactions. Okay, so one of the work I like a lot about Shuai is a paper he published in this year's OSDI, so where he shows that there's a lot of gains to be had when you combine the consensus and the transactions logic together. So given his background, so I'm really looking forward to how Shuai explains a fairly complicated subject of Byzantine Paxos in a very accessible way to the audience. Okay, with that, Shuai, please.
Okay. Thank you very much for introduction, Cheng, and hello, everyone. First, thank you very much for coming to this. I cannot really see you because I only have one screen, so I only seeing my slides. But I think that's fine. So today we're going to discuss how to, inject Byzantine failures into Paxos protocols and how can we tolerate those failures, reaching consensus. This is a old topic, has like 20 years of history. There is a very famous paper called Practical Byzantine Failure Tolerance, published by Castro and Liskov in OSDI 99. So in today's discussion, we're actually going to refine Paxos step by step. Eventually, we will have a protocol that is very similar to PBFT. So for today's discussion, I would like to go through 4 parts. First, I want to introduce very briefly on the background, why we need consensus and why we need replication, and all the assumptions and challenges we have to achieve consensus. And second, I want to go over Paxos protocols really quick, so you guys can refresh your memory about how Paxos worked. And for the third part, I will try to, tolerate some failures, some liars in Paxos, not all complete, protocol. And in the fourth part, I will tolerate all the lies in Paxos. So let's first go through the background. Why we need consensus? So actually what we need is replication. We usually, when we build a system, we want to achieve reliability, we want to have multiple replicas of the same data. For example, if we have the same database, we want to have 3 replicas, and we're trying to make all the replicas in a consistent state all the time. That's what we're trying to achieve. With these replicas, we want to tolerate some kind of failures. If one replica crash, we still have other replicas. And it's also important for us to make progress if there is some failures. So this replication problem can be abstracted as a replicated state machine. So it's a very classic abstraction. So if we have one program, it can be abstracted as a state machine. And then if we get replicated, become a replicated state machine. So the state machine takes a command as input and transition into another state and keeps going like that. So what we really need here is we need all the state machines, the replicated state machines, to do exactly the same state transitions for each step. In other words, we want to make a series of decisions, which command we're going to execute for the next step. For example, if we have two commands, two users, Alice and Bob, both trying to modify the same data in the system. So what we're trying to do here is we're trying to make a decision which command comes as first and which command comes as second. So this problem, making a series of decisions, is essentially equivalent to making only one decision. If we can make one decision, we can make a couple of decisions. So why making a decision is a very difficult problem in our setup. First, we assume asynchronous message passing model, which means any message can be arbitrarily delayed or lost in the system. And second, we have to tolerate failures in the system. To start with, we tolerate the easiest kind, the crash failures. A server can crash and stop responding to you. But even with this simplest kind of failures, plus asynchronous network, it makes this problem very difficult because we cannot actually detect the failures. If a server stops responding to us, we don't know if that server crashed or it's simply the message got delayed or lost. So with all these assumptions, this problem is a very difficult problem. And there is actually a classic solution to this, which is Paxos. So let's today make this problem even harder to solve. Let's bring in Byzantine failures. Let's try to make the failures more complex. Byzantine failures means that in the system, beyond simple crashes, the server can actually do whatever it wants to do. It can send out any message not following the protocol you have. This can actually happen in reality because the server might be taken by a malicious hacker, and then the hacker can just run arbitrary commands with that the program. Or it could happen only with some unexpected failures, in network and disks, because these components are not always behaving like, what they say they're going to do, like the spec, because there could be many human bugs there. So it is important to say that we're not trying to protect all the kind of malicious attackers. For example, if a hacker hacks the system and but it just issues a command following our protocol, but this command is harmful. For example, it is trying to delete the entire database or delete a very important table, but he's following the protocol. This kind of attack we cannot protect. We can only protect the system to be in a consistent state, that all the replicas are the same. So if a server can send arbitrary message, it is very difficult to tolerate all kinds of Byzantine failures because, for example, if I am a correct guy in the system, but if anyone else can pretend to be anyone else, meaning they can send me a message saying this is a message from another one, then I really cannot tell whether this is true or not, which means, for even one malicious attack, server in the system, he can pretend to send broadcast message to pretend everyone is malicious. So then this problem will be too difficult to solve. So we need to restrict the failure models by a little bit. So we assume that message cannot be forged, meaning you cannot pretend to be another guy. So this can be done in many ways. One classic way to do this is to introduce signing, the classic public and private key. So everybody will sign the message with its private key, and everyone knows the public key of everyone else, so it can validate this message is or not from, is genuine or not. So there are lots of optimizations can be done here to make this process faster, but we're not going to cover that today. We're only assuming that a message cannot be forged. Someone cannot pretend to be another one. So, okay, we now have done with background. Let's next review the Paxos protocols a little bit because we're going to refine based on Paxos, step by step. So the Paxos trying to solve the problem, making a decision, and its classic model includes proposer, which are trying to propose a value, to acceptor. Acceptors are trying to make a decision, vote for a value. So eventually, if a value is voted by a majority of acceptor, that value gets chosen. And finally, the learner is trying to learn the chosen value. So this is the classic Paxos model. But here today, to simplify our discussion, we only assume there are acceptors in the system, but acceptors actually doing the job for both proposer and learner. So the acceptors can be thought as the servers in the system. So in a high level, Paxos contain two phases. So there are names for the two phases, but we are only use phase 1A, 1B, 2A, and 2B to represent the phases. So in general, the one acceptor, the proposing acceptor, should send a 1A message, broadcast a 1A message to everybody. And upon receiving a quorum of replies, which is the 1B message, upon receiving a quorum of 1B message, it will do the phase 2A message to everybody. And everybody will broadcast its phase 2B message to everyone, and then the value gets chosen. This is how usually it works. So more specific, in phase 1A, the proposing acceptor or the ballot leader choose a unique ballot number, B, and broadcast the phase 1A message. And on receiving that phase 1A message, acceptor first checks if this is the highest ballot it ever sees. And if so, it will reply a phase 1B message with the highest ballot value it ever voted so far, or simply nothing if it hasn't voted. And upon receiving a quorum of phase 1B messages, the initial acceptor will choose the value from the replies, choose the value with highest ballot. If nobody has ever voted before, it can choose its own value. And with that value, it sends a phase 2A message. And when receiving a phase 2A message, the acceptor, similarly, it will check if this is the highest ballot it ever receives. And if so, it will vote that value in this ballot B and broadcast a phase 2B message as acknowledgements. And for any other acceptor, if it receives a quorum of phase 2B messages, it will seize that value as chosen, and this protocol successfully finishes. The quorum here for Paxos is a simple majority. So the intuition why Paxos works include the following properties. So first, different acceptors cannot vote for different values in the same ballot. Within the same ballot, only one value can be voted for. And second, an acceptor can vote for different values in different ballots, which means, two ballots, the value the same acceptor vote for can be different. In other words, acceptor can vote for multiple values. And third, an acceptor can vote for value only if and only if no other value was, ever chosen or will be chosen. So, for example, let's see. In the first ballot, some acceptor trying to propose a blue value, but this process does not succeed. And so in the next ballot, let's see, assume it's a ballot 3. Another acceptor trying to propose a green value, and it doesn't see the blue value because it didn't succeed. So it got trying to, get the green value decided. But it also does not succeed, which means only less than a majority of acceptors, voted for the green value. So in the next ballot, ballot 4, another acceptor trying to revote, repropose the blue one, and it sees, and it succeeds in this ballot. So a majority of acceptors voted for this blue value. So in all the ballots after ballot 4, they will see at least one acceptor in the quorum that voted for blue value, so they can only vote for blue value again. So which means in all the ballots after ballot 4, they can only blue value can be voted and then can be chosen. So, okay, this is how Paxos protocol works. So now let's try to inject some Byzantine failures into Paxos. In this part, we'll start easier. So we are only tolerate some kind of lies in this protocol. So first, let's assume there are some malicious acceptors. We call them fake acceptors. So we have, let's say we have N real acceptors and F fake acceptors. In this system, nobody can tell which one is the real acceptor and which one is the fake acceptor. So the question is, can we still achieve consensus? If we can, how many real acceptors do we need to tolerate F fake acceptors? I will just give the conclusion. So in the best case, we need 2F plus 1 real acceptors to tolerate F fake acceptors, which means in total we need 3F plus 1 acceptors. And why is this? Why do we need 3F plus 1 acceptors? This is actually, not difficult to think. Let's assume we have a collection of acceptors and we have F fake acceptors here. So to tolerate these F fake acceptors, we have to have a protocol that can proceed without replies from F acceptors, right? So, but the question is, if we have a such protocol, we cannot really tell if we have F acceptors don't responding to us, we don't know whether they are actually the fake acceptors or simply, we cannot get in touch with them because of the asynchronous network, all the messages are lost. So which means there are actually some real acceptors, just we cannot get in touch with. So with this F fake acceptors in the protocol and F lost real acceptors, we cannot get in touch with. If we want to still be safe, we need at least F plus 1 another real acceptors in the system. Because if we don't have F plus 1, the F fake acceptors can actually take over the system and bring the system into inconsistent state. For example, if the F fake acceptors simply pretend to be, voting for a value, and then you think the value it gets chosen, but after that, the fake acceptors can deny they have ever voted for that value. Then the system is inconsistent. So that's the reason why you need 3F plus 1 acceptors at least. So looking at this picture, it reminds us that this F plus 1 real acceptors and F lost real acceptors actually, form the 2F plus 1 acceptors, what we did in Paxos. So the natural thinking is, can we just add these F acceptors into the Paxos protocol and adjust the quorum size in the Paxos protocol? So, we can be fine. So it works like this. So this naive solution, if we can have extra, fake acceptor in the system, but we just increase the quorum size. Previously we have the quorum size as Q. Now we have extra F fake acceptors. We can just increase the quorum size to Q plus F. So every 2, we call this a bias quorum. So now every 2 bias quorums will have at least F plus 1 acceptors in common. And those F plus 1 acceptors will at least contain a real acceptor. So for example, if let's set F to 1 here in this figure, let's set F to 1. And previously we have the quorum size as 2 with 3 normal acceptors. So now we have a quorum size of 3, and any 2 quorum will have 2 acceptors in common, and at least 1 acceptor is a real acceptor. So which means that acceptor is completely following the protocol. Can this work? let's simplify the problem for now. Let's assume that all the lies in the system, the malicious acceptor can only behave as responding to a message, cannot, it cannot behave as a leader for a ballot. It cannot propose value in a ballot. So if this is the, the problem, how can this work? So, yes.
Come back to the slides.
Sure.
Okay, so here you are saying that, okay, so you have 4 acceptors in the system, right?
Yes.
Okay, 3 of them are real, 1 is fake. Okay, and then the current size is Q plus F is 3 here?
Correct.
Okay. Okay, so then you're saying that any 2 currents will intercept by 2. That would at least include 1 real guy.
Yes.
Okay. Okay.
Is that mean?
Sure.
Do you want?
Just try to clarify. Yeah, I think that sounds fine. Yeah.
Yeah. Right. So if we have a quorum of 3, for example, 1, 2, 4, and 2, 3, 4, then the 2 quorums will at least 2 and 4 in common. So acceptor 2 is the correct one. Yes, right. Thank you for that. Okay, so now let's try to see what's happening with this. So, yeah. Right. Correct. Yes, that's.
For the classical Paxos, you would still have a quorum of 3, right?
Yes, that's right.
Okay.
But yes. So another assumption we have for this part is that because we assume that a leader acceptor cannot lie. Leader acceptor means the acceptor that proposed value in that ballot. So if that cannot lie, which means there's, they cannot lie in phase 1A and phase 2A. So a liar can only exist in phase 1B and phase 2B. So can the system works?
So right now you're trying to simplify the problem, assuming that there's no lie in the phase 1 in 1A and then 2A.
Correct.
Okay. Got it.
I'm assuming all the phase 1A message and phase 2A message are genuine in the system. Phase 1B and phase 2B messages can be fake messages. Okay, so the modified protocol example will work like this. So in the first phase, acceptor 1 proposing a value, not proposing value, send a phase 1A message to everyone else. And now there's no lie. Everyone just replies the correct thing, assuming there are no value ever voted before. And so the acceptor 1 can go on into phase 2, and in phase 2 it includes this blue message, this blue value, and send a phase 2A message to everyone. And assuming that the other acceptors, acceptor 3 and acceptor 4, will reply that I vote for this value and reply phase 2B to acceptor 1. And acceptor 2 here, it doesn't receive the message of phase 2A, so it does nothing. So let's assume after this, acceptor 1 crash, right? Acceptor 1 crash, and now.
So can you go back to the slide, the question here? Okay, so here you are assuming acceptor 1 also accept its own thing, right?
Yeah, here I'm assuming acceptor 1. Thank you for that. Assuming the message also comes to itself and it also, agrees with itself and send all the 1B and 2B messages.
Okay, so in both phases, you have quorum of 3 satisfied.
Right.
Okay.
So in both phase, we have quorum 3 replies. So this is the setup. So the lie has not come out yet,
Okay.
right? So this is the setup. So let's assume after accept 1 finishes its ballot, it crash here. So now acceptor 2 comes out and trying to discover, what value has been chosen before by redoing this this 2 phase for the next ballot. So for the next ballot, in phase 1, it sends a phase 1A message to everyone else. Acceptor 1 crashed, so it cannot respond. So acceptor 3 is a real acceptor, and it replies with a phase 1B message saying, I voted for the blue value in previous ballot, right? So acceptor 4 here is a liar. It's a liar, and it's trying to lie in phase 1B, saying, I voted for red value, right? So I voted for red value. So it replies phase 1B to the acceptor 2. And acceptor 2 has 3 replies from itself, but it hasn't voted for anything before. And the second from acceptor 3, which replies a blue value of the previous ballot. And acceptor 4 replies a red value for the previous ballot. But acceptor 2 now got stuck because it doesn't know which value to choose, the blue value or the red value. Only the blue value is the legal value it should choose, but here it cannot tell. So, which means, our naive solution by simply, increase the quorum to include the F fake acceptors don't work. Any questions on this? So, okay. So here comes the solution to this problem. Because we got stuck, because we got stuck because there is one genuine reply, there is a fake reply, and we cannot tell. Now, if we have like 2 genuine replies, let's outvote the liar. Let's have more, real acceptors in any case in replies than fake acceptors. So we can always tell the lie. So in that case, we can proceed even with the liar existed. So the solution is that we increase our bias quorum from 2F plus 1 to 3F plus 1, right? So in that case, any two bias quorum will have 2F plus 1 acceptors in common. And with that 2F plus 1 acceptors, there must be F plus 1 real acceptors. There at most can be only F fake acceptors. So the F plus 1 real acceptors can beat the F fake acceptors. For example, let's assume there's only one fake acceptor. This acceptor 5 is a fake acceptor. And now we have the quorum as 3F plus 1 becomes 4, right? So any intersection will have 3. For example, this two quorums, and this is also a quorum. And these two quorums will have acceptor 2 and acceptor 4 in common, right? So there are at least 2 acceptors in common. They can outvote the lying acceptor, acceptor 5. So
any 2 quorums will have three. Any 2 quorum will intercept with 3 guys. Okay, so 2 of them would be real, then 1, at most, 1 would be fake, so 2 would be real. That's the setting, right?
Right. So
okay.
With the 2 real acceptors, we can, they can come up with a decision that is, outvote the lying acceptor. Okay. So now let's go over the example again and see whether this works. So the setup is the same. So acceptor 1 successfully gets the blue value chosen with its own ballot, phase 1, phase 2. But acceptor 2 does not receive the message of phase 2A. So it doesn't know which value to vote for. So after that, acceptor 1 crash. And now acceptor 2 and trying to redo these two phases in its own ballot. It broadcasts a phase 1A message in the higher ballot to everybody. So it itself doesn't vote for anything in previous ballot, so itself can not respond any value. Acceptor 1 crash, so it cannot respond. So acceptor 3 and acceptor 4 will return the blue value, right, as a phase 1B response. Acceptor 5 here is still lying, and still lying, it still returns a red value, which is a fake value. But now acceptor 2 with 4 replies, in the 4 replies, it has 2 blue values and 1 red value. Then it can choose the blue value because it wins over the red value. So now this protocol actually works. So by simply increasing the size of the quorum.
In this case, don't you still need a 4 replicate as to form a quorum in this case?
Yes, you do. So the 4 replicas including itself. So 1, 2, 3, 4.
But only two of them voted for blue.
Yeah. So the protocol works like you examine the replies from the quorum, and you pick the value. If the replies give you any value that has, you pick the value that is, more than has a, how can I say this?
So I think the question is, acceptor 2 knows what is the right thing to do, but it still cannot make progress, right? Because it cannot get its message chosen, right? Because if 1 is not responding, 5 is responding something else, will 2 be able to get its value chosen?
Oh yes. Well, what do you mean is can acceptor 2 acceptor 2 knows to propose the blue value, but can acceptor 2 get the value chosen?
Yes.
In the future. So it's the liveness problem. The answer is no. In this case, if you don't recover acceptor 1, so if you don't recover acceptor 1, acceptor 5, and acceptor 5 keeps not cooperating, then you cannot have the value chosen. So because you only have 3 quorums that are working following the protocol. So I think that's an interesting question. My understanding, I actually don't know which is the correct answer, but my understanding here is that the liveness can only be guaranteed like eventually, because it's actually a partial asynchronous network. If in this case you cannot make progress because there is not enough real acceptors in the system. So, but if you guarantee that there will be enough real acceptors in the system, and all the message will be eventually be delivered, then with that assumptions, you can make progress eventually. So that's my understanding.
Yeah.
Chen, what do you?
I think this sounds interesting, right? Because from here, 2 can immediately tell that 5 is a liar. then somehow you should be able to just move forward, because if 5 is a liar, then 3 out of 5 would just allow you to make progress, right?
But 1 can become a liar, presumably, no? Like, you could have acceptor 4, then becomes a liar.
Then this wouldn't work anyway, right? Because if you had 2 liars out of the 5 system, it's not going to work anyway. So the assumption is here it only tolerate 1 lie. So I don't know if there's additional subtlety preventing this from to work. Right? If you can identify 5 as a liar, then you can just assume this is a quorum that 5 is a real guy but just dead all the time. You ignore all its messages. Then, so you have 3 out of 5. Then, could you just make progress on the liveness part?
So I think for the liveness, there is another thing is that if you have a lying acceptor in the system, and if you allow that acceptor to propose value, to issue command, then probably you will never get liveness. So because, it can just go on, and trying to reproposing as if it never gets succeed. So
also, he might not be a liar. He might have been lied to. He might be passing on incorrect information he got from a liar. A lying proposer.
Could that happen?
Proposer can't be liar, right? That's the assumption.
Oh, okay.
So,
That's the current setup.
Right, but in real BFT, you can't.
Yeah, so I think the try is going to relax that, but at least at this moment, you're assuming the proposer cannot lie.
Yeah, if you can trust the proposer.
yes. So, okay. So,
I think it's interesting to think about.
in addition, this is only a transition. This is only something in transition. We are actually not use this thing in the end. But why? Why is that? Because this protocol has a very big problem. It requires many acceptors, right? In total, it requires like 4F plus 1, which is much more than what we hope for, 3F plus 1. So the question is, can we reduce the number of acceptors to 3F plus 1? If we look at the problem, we find that alternative solution is that instead of we tell the lies, we tell between which is the liar, we can choose to find a way to disable the lies in the beginning in the phase 1B. So if we can require phase 1B message be attached with a proof. So the proof means that this value was actually a safe value, not a fake value. If we can ask phase 1B message to attach that, then we can actually disable the lies in phase 1B, right? Because it cannot forge a proof. And the proof we are looking for is actually implied by phase 2A message in the previous ballot. Because if in the previous ballot, if the phase 2A message was ever sent out, then it means that the phase 2A, this value was actually proposed by the leading acceptor in the previous ballot, right? So if we assume there's no live phase 2A, there is no fake phase 2A message in the system, then we can do this in an alternative solution. So let's look at this example again. So, okay, first the setup is the same. Acceptor 1 successfully gets the blue value chosen, and then after that it crashed, and acceptor 2 comes out to redo the two phases, and after it broadcasts the phase 1A message, itself it hasn't voted before, so nothing. So, but acceptor 3 has voted for the blue value, so it will reply the blue value. And in addition to that, in addition to replying the blue value, it will reply this phase 2A message it received before as a proof that this is the real value. And acceptor 4 here trying to lie, is still trying to lie with the red value, but because it never receives the phase 2A message for the red value, it only received the phase 2A message for the blue value. It cannot attach a proof with its phase 1B message. So after acceptor 2 receives this, it can tell that the red value is a lie because it does not come with a proof, right? So all this work because we assume that the phase 2A message is it must be real. No one, an acceptor cannot lie about phase 2A message, and we also assume that the acceptor cannot forge another guy's phase 2A message, right? So this is why this works.
Hold on a second, let me try to understand. So yeah. I think you are saying that because you use digital signatures, so that
right.
2A message cannot be faked.
Correct.
Okay. So that's why when 3 send the 2A back, then 2 can verify that's a real 2A, but 4 cannot somehow fake a real 2A out.
Yes.
Okay, got it. Thanks.
Okay. So and then acceptor 2 can go on with the original protocol. So I have a few open questions for this. Now we assume that phase 1B all attached with the previous phase 2B, phase 2A as proof. But the question is, can acceptor still lie without being caught in this phase, right? So, if can still lies, does it hurt? And also, we only talked about the lies in phase 1B. What about the lies in phase 2B? So these are all like simple but interesting questions. I don't want to spend time to cover today because this can cost another 30 minutes. But I would like you to all think about this because these are interesting corner cases to think about. In general, the acceptor can still lie in phase 1B, but it won't hurt. And also, the lies in phase 2B also don't hurt. Okay, so we have finished the previous part with limited lying, but now let's complete the protocol. We allow liars to lie in all phases, including phase 2A and phase 1A. So let's see how this thing can work. So if we assume an acceptor can lie as a leader for a ballot, what we're actually talking, it can lie in phase 1A and phase 2A. If you think this, harder, you find out you actually cannot lie in phase 1A because phase 1A is like you don't have options for phase 1A. The message is single formed, so you either send or not send the message. So lying in phase 1A actually don't matter. So the thing that matters is if that you lie in phase 2A, you fake a phase 2A message. So for example, you can you received some message from phase 1B, you actually should be proposing the blue value, but now you can actually propose in the red value, and the acceptors receiving this phase 2A message will just unconditionally vote for this red value because it has the maximum ballot. So this is really bad. So the lying actually matters is the lying in phase 2A. What we do to cover the lying in phase 2A, first, let's make the problem easier by breaking phase 2A into two phases. We add one phase, that's phase 2C. Phase 1C. So why we're extracting phase 1C from phase 2A? Because the phase 2 actually function as has two functions. One is assert that a value is safe for this ballot, and two is to instruct the acceptor to vote for that value. So let's extract, let's divide these two functions. Let's use phase 1C to assert some value is safe for that ballot, and let's use phase 2A to instruct the other acceptors to vote for that value. For example, in this case, after acceptor 1, receive enough phase 1B message and trying to determine which value to propose, it first sends a phase 1C to everyone saying, hey, this blue value is safe. And next sends a phase 2A to everybody, say, hey, please vote for this blue value. So now let's assume there's no lie in phase 1C, only lies in phase 2A. Let's first solve the lies in phase 2A. So
shall I have a question?
Yeah.
So the 1C message goes out, there's no response, right? You're not waiting for... Response. Okay, so you're just doing 1C and then after that you're doing 2A?
Correct.
Okay.
And now we assume that phase 1C are all genuine.
Okay.
Phase 2A can have lies. Okay. So the way to deal with the lie in phase 2A is to have it work cooperatively. So you can actually deduct the correct phase 2A message. So let's say the leader acceptor for that ballot sends a phase 2A prime request with a value V, that the value is trying to, have everybody to vote. So on receiving that phase 2A prime, an acceptor will check if it's the highest ballot. And if so, it will do another check, say if that value is safe. By safe, it means that if I have received, a phase 1C message for that value, because for now we assume that all phase 1C message are genuine. There's no lie in phase 1C. So if we have received phase 1C, means that V is safe. So after that, it will broadcast a phase 2AV message to every other acceptor. So, and acceptor receives that phase 2AV message, will check if it's highest ballot, and if so, then it check if I have received 2F plus 1. 2F plus 1 now is a quorum. If I received a quorum of phase 2AV message, asserting 2AV message trying to, on the same value. So if I have received a quorum of 2AV on the same value, I will pretend as if I received a real phase 2A message. Pretend I received the phase 2A message and do what I used to do for phase 2B. So in this way, I can disable the lie with phase 2A. So let's see example. Let's see. So first, acceptor 1. Acceptor 1 go through the phase 1 correctly and gets the blue value. Say the blue value is the value it should continue with phase 2. And it sends phase 1C of the blue value because it cannot lie here for now. We assume that. And after that, it sends the phase 2A prime to everybody else. And here it lies to one acceptor 2, that I want acceptor 2 to, go with red value. For every other acceptor, it goes with correct value, the blue value. So on receiving that phase 2A prime, the acceptor 2 here actually will check with its previous phase 1C message. It finds that the two values don't match, so it will not continue. It will stop there. For every other acceptor, because the values match for phase 2A prime and phase 1C, they actually match. So they will broadcast a phase 2AV message to everyone. And on receiving those two phase 2AV message, after acceptor receives a quorum of these messages, it will check if the message match with each other. And if so, it will reply phase 2B message or broadcast that to phase 2B message to everyone. So here, even for acceptor 2, who received a red value or wrong value previously, because it receives a quorum of, phase 2AV with the same blue value, it can reply the phase 2B message to everyone. So with this cooperative phase 2A, we can tolerate lies in the original phase 2A. So okay, any questions? No. Great. So now let's deal with the only problem left. How can we tolerate lies in phase 1C? Because it seems so far that what we can do earlier are totally depend on there's no lies in phase 1C. So how can we do that? The way to tolerate lies in phase 1C is actually similar to what we did earlier with phase 2A, because we see from this figure, we can see that acceptor 1 receives a quorum of replies phase 1B, so it can go on with his phase 1C. So if we can let every acceptor repeat the process, we let every processor repeat the process how the ballot leader sends its phase 1C, then we can, prevent the leader from lying about it. So the way we do it is like this. So every acceptor will broadcast its phase 1B message instead of just reply to the leader acceptor. And for another acceptor, if it receives a quorum of phase 1B messages, it can know which 1C is the real 1C, right? So it will next, when it receives a phase 1C message, it can, do the deduction itself and sees if this phase 1C message is legal. So, for example, for the same example, let's see, the acceptor first sends phase 1A message, and here in phase 1B, so every acceptor, instead of just replying to the leader, it will broadcast its phase 1B message, right? So, so everybody can know which value is actually safe, or collection values that are safe, and then acceptor 1 trying to do the phase 1C. Sorry about the slides. The red should be here, so this one should be red and this one should be blue. So let's assume in phase 1C, acceptor 1 trying to lie to acceptor 2, and acceptor 2 receive the red value. It will actually compare with its phase 1C, and this value does not pass because this phase 1B it receives does not match with its phase 1C, so it can tell the lie from phase 1C. So it won't acknowledge this phase 1C as real, and for the following phase 2, it will work like it never received that phase 1C. Sorry, this slide might be a little messy, so if you have any questions.
So I think what you're saying is by broadcasting 1B, every acceptor can just figure out what to expect in a 1C message. Okay.
Yes.
So in that case, do you still need to send 1C at all?
So I think it can be optimized, but I also think there is some other thing here, because legally, acceptor can send different 1C to all acceptors. But I think you get a point. You actually don't need to send 1C here. I think the purpose of keeping 1C here is later we want to convert our thing to be PBFT. So, but I'm not sure of that if we don't want to convert our thing to PBFT, whether we need 1C or not. In original Paxos, we don't need, because it's implied by the phase 2A, right? But here, I don't know whether we need 1C or not, if we are not trying to convert to PBFT. Okay, it's also hard to find out from Lamport's paper, because what I'm presenting today in my slides are not 100% consistent with Lamport's paper. It's more. I think many of them is my understanding, because
link or to the TLA plus specification, right, of that original Byzantine Paxos protocol. So we could look at that one, or even try to play with that to see if there's any issue if you don't do that.
Yeah. Okay. So there are 3 papers. The first paper is the PBFT, the original papers, cache release code from OSDI 99. So I read that paper. I think that paper is heavily related to, view stem replication. So I think it's hard to understand why it's correct from itself without understanding view stem replication. And the second paper is from the Lampert's Byzantine Paxos. Is actually most of these slides is about, right? But that paper is very short, so you also cannot have all the information from that paper. So yeah, the third is the TLA spec Lampert's provides. That's the 3 materials. Actually not the third one. I haven't spent enough time on the third one. Okay. So okay, yeah, that's a little bit background information for the papers. Yeah. So this is it. This is how we tolerate lies in phase 1C. So now we have tolerate lies in all the phases 1A, 1B, 2A, and 2B. So this protocol should be working fine with Byzantine failures. So let's add more, make it more practical. So like multi-Paxos, the phase 1 can be actually batched for multi-instances, right? So let's assume we have 100 instances. We only need to do the phase 1 for once. And for all the rest of the instances, we actually only need to do phase 2, right? The phase 2A prime, instructing cooperative phase 2 AV and phase 2B as a reply. So this is how the protocol can work in practice, right? So the interesting thing is if we rename the phase names and acceptor a little bit here, we get very similar stuff to PBFT, right? So the phase 1A is actually not explicitly sent in PBFT. It is, implied by timeouts. And the phase 1B message is a view change message in PBFT. And the phase 1C is the new view message in PBFT. And the phase 2A prime is pre-prepare, and phase 2AV is prepare, 2B as commit. So I think this is why we are naming the phases using 2A, 2AV, 2B instead of, accept request, acknowledgement, a prepare, a promise, the usual terms the Paxos use, because the Paxos, the same term prepare and means differently in Paxos and PBFT, right? The preparing PBFT is actually in phase 2, so it's more like an accept message, right? So, okay. So, do you have any questions, or no? Great. So let's take a summary, have a look back what we did to refine Paxos to PBFT. So first, we introduced some fake acceptors to Paxos, and we changed the definition on the quorum. So, and we enlarged the quorum to tolerate the fake non-leader acceptors. And to shrink the quorum, we attached a phase 1B message with previous phase 2A message to shrink the quorum. So, and next, to tolerate the lies from leader acceptors, we extract phase 1C from phase 2A, and then using this phase 1C message, we make the phase 2A into a cooperative phase, right? And then we broadcast phase 1B to allow every acceptor to deduct phase 1C. Then we prevent the acceptor lying in phase 1C. and then we put the multiple instances together with batched phase, and we come with the actual protocol that can be, is very similar to PBFT. Why I see similar, because we are, omitting the client concept. In PBFT, you have a client, then you have replicas. In our discussion, we assume the client is on the same machine on the server of the servers. Okay, I think that's all of my content. Thank you very much.
Great, Frank. Yeah. Thanks a lot. So this really feels subtle. I want to check the audience if there's any additional questions. Okay, sounds like we covered the questions during the presentation. So
okay, great.
Why don't we thank the speaker again? Yeah, thanks a lot, Frank.